So, what happens when a router receives an IP packet that is larger than the next Layer 2 MTU? That's where another responsibility of IP comes into play. IP was designed to accommodate these differences through a process called fragmentation. If a packet is bigger than the MTU of the Layer 2 technology, a device might need to break the packet into several pieces or fragments. The fragments are then sent individually and reassembled into the original packet by the receiving device. When host A begins generating packets, it checks the MTU for its local network, which in this case is 1500. As the packet crosses routers, each router checks the MTU for the next network in the path. If the network has a smaller MTU than the current packet size, the router fragments the packet into smaller pieces. Each fragment contains an IP header that duplicates most of the original header, followed by as much data as can be carried to keep the total length smaller than the network's MTU. The fragments are now sent as separate packets until they reach the destination, where they are reassembled by host B. You are now familiar with the structure of IPv4 addresses which are used in most home and business networks. Unfortunately, the pool of available IPv4 IP addresses has almost been exhausted. As a result, an increasing number of research and educational facilities, service provider, and corporate lab networks are using the next generation protocol, IP version 6 or IPv6. The major difference between the two is the size of the address. IPv6 addresses are much larger, 4 times larger than IPv4 addresses in fact. The larger address size means we won't exhaust the supply of addresses for many years to come. In fact, in IPv6, just one /64 subnet has more addresses than the estimated number of grains of sand on all the beaches on the Earth. IPv6 was defined by the Internet Engineering Task Force and standardized in 1998. In case you are wondering why IP went from version 4 to version 6, there was actually an experimental protocol named Internet Stream Protocol, which was considered by some to be IPv5, but this never came to be. The protocol never made it past experimental stages. Although address exhaustion was a major reason for development of IPv6, it provides several other improvements over IPv4 as well. IPv6 eliminates the need for Network Address Translation, or NAT, which in IPv4 allows multiple private IP addresses to be hidden behind a single address. With the huge number of IP addresses available in IPv6, NAT isn't needed or supported. IPv6 reduces administrative overhead. Hosts can use Stateless Address Auto-Configuration, or DHCP-v6, to assign an IP address to themselves. It supports greater levels of security by integrating features that were optional add-ons in IPv4. IPv6 also makes processing more efficient in a number of ways. You'll understand how this is achieved as we look at the changes in frame format between IPv4 and IPv6. One of the main changes in frame format in IPv6 is that the header is now a fixed length. IPv4 headers have an options field of variable length, which means the total header length can vary from 20 bytes to as much as 60 bytes. The IPv6 header eliminates the options field and uses a fixed length of 40 bytes. This is one of several features that make IPv6 processing more efficient than IPv4 processing. While the IPv6 header may be longer than many IPv4 headers, the router does not need to spend time figuring out which part of the packet is the header. Because IPv6 addresses are much longer, the source and destination IP addresses take up much more of the header. However, other fields that were included in IPv4 are eliminated in IPv6, decreasing the space needed for the rest of the fields in the header. Let's look at some of the fields that were removed. The IPv4 field IP header length was removed in IPv6 since the IP header length is always the same. IPv4 has a header checksum field that provided a means of error checking on the IP header itself. IPv6 removes this checksum, which means there is again one less thing for the router to do when processing the header. In IPv6, error checking takes place at layer 4 when the frame is processed at the endpoint, and not while it is en route to its destination. IPv4 provides several fields that are used when a router fragments a packet: identification, flags, and fragment offset. These are removed in IPv6 because IPv6 routers do not fragment packets. Instead, hosts are responsible for dividing the data into appropriately sized packets before sending them. Again, you can see that functions performed by IPv4 routers are offloaded in IPv6, with the result that IPv6 routers can process these packets much more efficiently. The IPv4 protocol field specifies the number of the layer 4 protocol used in the data portion of the packet. In IPv6, the protocol field is replaced by the next header field, which plays a similar role, but in a new and expanded way. Let's take a moment to look at this important enhancement. In IPv4, the protocol field specifies the number of the layer 4 protocol used in the data portion of the packet. For instance, if the protocol field value is 6, a device inspecting this packet will know that the next header within the packet is the header of a frame being transferred by TCP protocol. In IPv6, the protocol field is replaced by the next header field, which plays a similar role, but in a new and expanded way. IPv6 supports a variety of optional extension headers that extend functionality. In the example shown here, the IPv6 header's next header field says that the next header is type 0, which specifies one of the extension header types defined in IPv6, a hop-by-hop options extension. That extension contains its own next header field that says the next header is type 44, which means it is a fragment extension. That extension also contains its own next header field, and it says the next header is type 6, which means, just as it does in IPv4, that the content is a frame being transferred by TCP protocol. 6 extension headers are currently defined: hop-by-hop options, destination options, routing, fragment, authentication, and encapsulating security payload, or ESP. The destination options header can appear twice in a packet as shown. Each extension specifies the type of header that follows. The packet depicted on screen shows all extensions added in the preferred order. Other types of headers may be added in the future. Click any of the extension headers to learn more about its function. Click Continue when you are ready to move on. Now, at this point, you may think, wait a minute, doesn't the addition of extension headers negate the gains in processing speeds made by having an IPv6 header that is always 40 bytes? The answer is no, because in most cases, these extensions are only examined by endpoint devices, not by routers. The primary exception is hop-by-hop options, which contain options that need to be examined by all devices on the path. Also, in mobile networks, routing headers may be processed by intermediate devices. Continuing with our comparison between IPv4 and IPv6, let's look at the fields that serve essentially the same functions for IPv4 and IPv6. The value of version is simply changed from 4 to 6. IPv4's diffserv field, which allows for traffic prioritization, is called traffic class in IPv6. IPv4's total length field, which specifies the entire packet size, is called payload length in IPv4. IPv4's time to live field, which prevents packets from persisting indefinitely on a network, is called hop limit in IPv6. The size of source and destination addresses increase from 32 bits each to 128 bits each in IPv6. There's actually only one entirely new field in the IPv6 header. The new flow control field is used for quality of service management. After all these changes, here is what the IPv6 header looks like. Click each IPv6 field for a reminder of what function it serves. To compare the IPv6 header with the IPv4 header you saw earlier in this course, click the link on screen. Let's take a closer look at IPv6 addressing. At first glance, an IPv6 address can look alarmingly complicated. IPv6 presents a 128-bit address in 8 16-bit hexadecimal sections separated by colons. However, IPv6 does allow for abbreviation. Consider this example. You might think that you are looking at 3 different IP addresses, but in fact, you are looking at the same address displayed 3 different ways. 4 consecutive zeros in an address can be identified as a single zero. You can also omit leading zeros from the notation. A double colon can replace consecutive zeros, leading zeros, or trailing zeros. However, you cannot use a double colon twice in an address notation. Doing so will result in the misinterpretation of the IP address. IPv6 addresses are not case sensitive, so this 4th example also represents the same address. Now, imagine that you need to search for this address through a Unix system. If the address appears in several different formats, you might need to use regular expressions to find all matches for the address. However, many applications exist that do not provide this capability. Spreadsheet applications and many text editors often do not have the ability to search for text using regular expressions. And many people who need to manage IP addresses may not know how to use regular expressions either. For this reason, the Internet Engineering Task Force developed a set of recommendations for how IPv6 addresses should be consistently represented. Our 3rd example follows these recommendations. The standards put forth in RFC 5952 specify that leading zeros must be suppressed. The use of the double colon symbol must be used to its maximum capability, and all letters should be represented in lowercase. There are a few additional requirements as well. The double colon symbol must not be used to shorten just one 16-bit field. In the example shown here, the first example is incorrect because it has 4 zeros in a row which have not been condensed. In the second example, the address is condensed using double zeros. This is permissible in IPv6, but it does not meet the standards outlined in RFC 5952, which specify that the double colon symbol must not be used to shorten just one 16-bit field. These standards reserve use of the double colon to replace multiple 16-bit fields consisting of all zeros. The third example is correct. A single 16-bit field full of zeros is condensed to a single zero. When an alternative choice exists in the placement of a double colon symbol, the longest run of consecutive 16-bit zero fields must be shortened. In the example shown here, the address has one run of two 16-bit 0 fields and one run of three 16-bit 0 fields. The correct representation is to condense the set of three 16-bit 0 fields using the double colon and condense the two other 16-bit 0 fields using single zeros. When the length of the consecutive 16-bit 0 fields are equal, the first sequence of 0 bits must be shortened using the double colon. The address shown on screen has two runs of two consecutive 16-bit 0 fields. The first one must be shortened using the double colon. The others should be shortened to single zeros. The document specifies that this format should be followed by people and systems when representing IPv6 addresses as text, but systems should be able to accept and handle any legitimate IPv6 format. We recommend that you follow these recommendations when writing an IPv6 address. While IPv4 and IPv6 addresses look quite different, their structures are actually very similar. In both cases, a prefix length given at the end of the address specifies which portion of the address is the network prefix. Let's add all of the zeros back into the IPv6 addresses in these next few examples so that they are easier to compare. Now you can see more easily that in the /24 IPv4 address, the first 24 bits are the network prefix, and in the /64 IPv6 address, the first 64 bits are the network prefix. In an IPv6 address, each of the characters represents a 4-bit binary number. In both IPv4 and IPv6, the network prefix is followed by the host portion of the address. However, in IPv6, this portion of the address is most commonly called an interface ID. In an IPv6 address, the network prefix is broken down into two sections, a global routing prefix and a subnet ID. The global routing prefix is typically assigned to you by your ISP or by your regional address allocation entity. The subnet ID is set and managed internally. The process of subnetting IPv6 addresses is basically the same process as subnetting IPv4 addresses. Remember that subnetting is used to create multiple broadcast domains that are smaller than your entire network. For instance, you may decide that you only want to have a certain number of hosts in each subnet. You create a subnet by changing the mask assigned to each broadcast domain. Your global routing prefix does not change. By extending the length of the subnet ID, you will have fewer hosts or interfaces in each subnet. In the second example shown on screen, the /116 prefix length leaves 12 bits for the interface ID. This will allow for 4,096 addresses in the subnet. Note that the first address starts with 1 and not 0. In IPv6, the first address in a subnet or host ID 0 cannot be assigned to any device because it is the Anycast address. A packet sent to this address will be routed to the nearest interface in that subnet. The only exception to this rule is when you are defining a /127 prefix length for a point-to-point link. A /127 prefix length only allows for two IPv6 addresses, so you will need to be able to use both of them. Note also that because IPv6 does not use broadcast, you can use the last address in the subnet as a valid interface ID. Now, say that you would like to create a smaller subnet. If we extend the prefix length by 4 more bits, there are only 8 bits left for the interface ID, which will allow for 256 valid addresses in the subnet. But maybe that isn't enough. What if you wanted to create a subnet that had more than 256 addresses, but less than 4,096? To visualize the subnet mask for a prefix length that does not fall on a 4-bit boundary, you will need to look at the address in binary. Here is what the /116 address we showed you looks like in binary. We've added spaces so that you can see more clearly that each character in the address becomes a 4-digit binary number. Now, suppose we want to extend the prefix length by just 1 bit to a prefix length of 117. This leaves 11 bits for the unique IP addresses in this subnet. Here are the first and last addresses in the subnet range, shown in binary. And here is the range shown with binary converted back to hexadecimal. A subnet with a prefix length of 117 will give you 2047 valid addresses. Just like with IPv4, certain prefixes are reserved and should be used for specific types of traffic. RFC 4291 defines the latest rules regarding prefix notation. At this point, we now know how IPv4 and IPv6 addressing and subnet masking work. We learned about the different fields in an IP header, and we've seen how an IP datagram travels from a source device to a destination device using Ethernet as our Layer 2 networking technology. Do you remember how to represent IPv6 addresses following the requirements of RFC 5952? For each IPv6 address that appears, select the correct canonical short form of the address.